Welcome to the lesson on section 6.2, volumes of solids formed by cross-sections. In this lesson, you'll learn how to use integrals to find the volume of solids formed by stacking geometric shapes above a bounded region. Recall that in previous lessons, our solids of revolution have been formed by revolving a curve about a horizontal or vertical line. This process formed circular cross-sections with area pi times radius squared. In this lesson, our cross-sections may not be circular. They can be any other shape whose area we can calculate using geometric formulas, such as triangles or squares, but we'll still use the same principles to set up our integrals. Our integrand will still represent the area of each cross-section, and the dx or dy will still represent the thickness of each slice. In example 6, a pyramid measuring 3 meters high has congruent triangular sides and a square base measuring 3 meters on each side. Each cross-section of the pyramid parallel to the base is a square. We need to find the volume of this pyramid. In order to make this problem work for us, we need to be able to imagine the solid as many slices of similar shape standing up over a flat surface that we can describe using equations. If you imagine slicing the pyramid in half from tip to base and laying the half pyramid on its side, the flat surface we've created is the triangle you see in blue here. The half pyramid would look something like this tent. But imagine it lying down on the triangular side. The square base of the pyramid lies on the y-axis, and the tip of the pyramid is at the point 3, 1.5. Slicing parallel to the x-axis would give us thin rectangular prisms. In order to find a formula for the area of the face of each rectangular cross-section, we need equations for the sides of the triangle. Using the points given in the graph, we can find the equations y equals negative 1/2 x plus 3 for the upper side and y equals 1/2 x for the lower side. The thickness of each rectangular slice runs horizontally in my graph, so we're dealing with dx. The width of each rectangle is what y equals at the top of the triangular region minus what y equals at the bottom of the triangular region, or negative 1/2 x plus 3 minus 1/2 x, which simplifies to negative x plus 3. The cross sections of the pyramid are squares, but remember that we sliced the pyramid in half so that it would be flat on one side. So the height of each half square standing up over the triangle in our diagram will be half of the width we just found, or negative x plus 3 divided by 2. Since we cut our pyramid in half, we'll need to multiply our integral by 2. We've already determined we're writing this as dx, and the triangular region we're stacking the half squares above extends from x equals 0 to x equals 3. And the area of each cross-section is base times height, or negative x plus 3 divided by 2 times negative x plus 3. This is our volume. What you may want to do here is go ahead and calculate the volume of the pyramid geometrically. The volume would be 1/3 area of the base times the height, and compare to what you get from calculating this integral. Example 7 is problem number 58 from page 392 of our textbook. The base of a solid is the triangular region with vertices 0, 0, 3, 0, and 0, 2. Cross sections perpendicular to the y-axis are semicircles, and we need to find the volume. So start by graphing the triangular region. Here's what the semicircles might look like, and a sample slice. The area of each semicircle can be found by 1/2 pi times radius squared, and the thickness of each semicircular slice runs vertically, so our integral will use a dy. In order to describe the radius of the slices, I need equations for the sides of the triangle. The vertical side is x equals 0, and the diagonal side is y equals negative 2/3 x plus 2. The diameter of each semicircle can be found by what x equals on the right minus what x equals on the left. This means that I need the equation of the diagonal line written in x equals form. So the right side hits x equals negative 3/2 times y minus 2, and the left side of the diameter hits x equals 0. The radius is half of this. The integral describing this volume will be 1/2 pi, that's from our area formula, times the integral from y equals 0 to y equals 2, which are the lower and upper bounds of the triangular region, of negative 3/4 times y minus 2 squared. This was our radius squared, dy. This concludes our lesson on section 6.2, Finding Volumes by Cross-Section.